Okay, so this is the outline for chapter 21. Okay, so we will introduce what is Coulomb's law, and then I will also briefly introduce what is charges quantized, and also charges conservation of charge. Okay, but I just briefly talk about it, but it is nothing special. Okay, so first of all, let me try to introduce something like a simple experiment, or like an observations. So this title is a magic question mark. Okay, so here we have a couple of small experiment. Okay, so here it says the two glass rods were each rubbed with a steel cloth, and one was suspended by thread. When they are close to each other, they repel each other. So which means that if we try to connect this glass here, try to fix it, and then of course this glass is free to rotate, and then we have another glass rod. So we try to use a screw cloth to rub this one, and also this one, and then we try to put this one close to another one. This one is hanging here, and then there will be a force repelling them. This force will pushing the top one to the top left, and then pushing the bottom one to the bottom right. Okay, so that they repel each other. Okay, so this is the first observation for the first setup. First setup, and then for the second setup, we have replaced this glass rod by a plastic rod. So the plastic rod was rubbed with fur. So rather than rubbing it with a steel cloth, we rub it with a fur. And then we try to place this one close to the hanging glass rod. Then there will be a force attracting them, which means that there will be a force pushing the top glass rod to the bottom right, and then there will be exactly the same force with opposite direction acting on the plastic rod. So these two rods are attracting each other. Okay, so of course, we will try to consider it in a scientific way. So these are two setups, and then we try to change this rod to a plastic rod, and the phenomenon, the result are different. Okay, these two rods repel each other. These two rods attract each other. So there must be something internally different to make the result different. Okay, so the physician or the scientist will try to explain why it will be like that. Okay, and the answer is, okay, so here we will consider if we try to rub the glass with the steel cloth, then two charge rods of the same sign repel each other. So after rubbing the glass rod with the steel cloth, there will be positive charge. On both of the glass rod. And of course, during the primary class, you already know that the charge with same polarity will repel each other, so that these two glass rods will repel each other. And for this one, for the second setup, the physician will try to explain it like the plastic rod will have negative charge rather than positive charge. And then also in primary school, you know, opposite charges will attract each other. Of course, you may ask, why the glass rod will have positive charge and the plastic rod will have negative charge. But yeah, so far it is just some tiny set of for the observation. So you don't really need to remember why or where you don't really need to remember, oh, a plastic wad will have a negative charge rubbed it with the fur, and you don't need to remember, oh, with the glass wad you rub it with a skew cloth. These details, you don't need to remember these details. It's just an observations. Okay, so it says two glass wad of the same sign repel each other, and then a plus sign indicate positive net charge and the minus sign indicate negative charges. So here, okay, and this is the highlight. Particles with the same sign of electric charge repel, and the particle with opposite sign attract each other, or in short, same repel and then opposite attract, like that. Okay, so this is just something very simple. Okay, so the next part, we will try to talk about the classification of the materials in terms of conducting ability. So of course, I think even in primary school, you will try to know something about the conductor and also the insulator, 导体绝缘体. Okay, so you know that a conductor, a material in which a significant number of electrons are free to move. Example include metals. And also in the primary school, you also have learned the charge particle in non-conductors. Okay, so for sorry. Okay. Okay, let me go back. Okay, so okay, just now we mentioned that there will be conductor and also insulator. So conductor is so-called 导体. And the non-conductor or the insulator is so-called 绝缘体. So and for the conductor, there are some electrons are free to move, which means 自由电子, the free electrons. Free electrons. And for the insulator, there are few of free electrons. Yeah, are not free to move, but there should be a small amount, very, very small amount of free electrons comparatively. So for example, include rubbers, plastic, and glass. And between the conductor and insulator, there are something called semiconductors. Semiconductors are material that are immediate between conductor and insulator, include silicon, germanium, and computer chips. So in high school chemistry, you should have learned what is the periodic table. Periodic table in the chemistry class. So in the periodic table, on the left side, there will be metal, and on the right side there will be insulator, like something like the oxygen or something like the gas, which are insulator. And in between there are some semiconductor. semiconductor. Actually, I suppose you have few chance to learn about the characteristic of semiconductors, because the characteristic of semiconductors are very, very difficult. So for ECE students, they will have classes to learn about the applied electronics, about the MOS transistor, which is about the semiconductor circuit. And of course, I'm from the microelectronic lab. And yeah, also we will use the semiconductor circuit to have to design some semiconductor circuit for some specific functions like that. And yeah, the point is that of course the conductor has low resistance. Resistance, and I suppose you also have learned what is resistance in high school physics. So I suppose you should know a bit about that. And so of course, conductors is good at conducting or have low resistance. So it might be used for for being a wire, like transferring power or connecting the circuit element. But actually for the semiconductor, as it has a very complicated characteristic, then it will be useful for some complicated circuit like logic circuit. For example, for the ECE student will learn what is the MOS transistor, metal oxide semiconductor. So maybe if you are interested for constructing or building up a computer, then maybe you know what is BIOS. Then if you enter the BIOS, maybe you try to construct or build your own computer by yourself. You just go to the computer store to buy some GPU, CPU, something like that to build your computer. Then you might know what is BIOS. And in between, you should have read something like a CMOS, complementary metal oxide semiconductor. And this S is stand for semiconductor. And yeah, so actually the semiconductor can be useful for constructing like logic circuit. Like if you have learned something like the logic, maybe you will know maybe NOT gate. NOT gate is like A prime, y equals A prime. If the input is 1, then you output as 0. If you input as 0, then you output as 1. Then it's a NOT gate. And maybe an AND gate. If you have both input to be 1, then you will output a 1. If you have one of them is 1 or none of them is 1, then A and B will be 0. Something like that. AND gate, OR gate, something like that, or something like the logic gate. Then you can use the CMOS logic to build that kind of a logic circuit. And also you can use the semiconductor to build amplifiers. Yeah, maybe you can use the amplifier to amplify the analog signal. Yeah, to 放大器 amplifiers. Amplifier, 放大器. So yeah, so this is something like the analog circuit, and this is so-called the digital circuit. Okay, so semiconductor will be very useful, but its characteristic are quite complicated. So yeah, during the high school physics, you seldom have chance, or even though in bachelor study, except computer science or ECE, they seldom learn even those computer science, they might not learn the CMOS circuit. but I'm not really sure for here. Yeah. But yeah, so actually semiconductor circuits are quite complicated, which that's why in high school chemistry or high school physics, they seldom talk about it. And the last part, superconductor, even less possible to mention it because even though me, I don't know much about the superconductor, but simply speaking, the superconductor is something like it has perfect, it is a perfect conductors. It exactly zero resistance for the superconductor. But to have superconductor phenomenon is very, very difficult. You must achieve a very, very low temperature, close to 0 Kelvin. I suppose you should know the absolute temperature. This is not okay. This is 0 Kelvin. The absolute temperature. 绝对温度. Okay. So I suppose you in high school physics, you have learned what is absolute temperature, the Kelvin. The Kelvin, 0 Kelvin is around negative 243 degrees Celsius. So you are familiar with degree Celsius. So Kelvin is linear. It's linearly with the. You just need to add 273. Then you transfer the Kelvin into degree Celsius. So you need to achieve very, very low temperature, around 0 K. At least when the physician or the scientist discovered the superconductor phenomenon, it need to use the liquid helium. The liquid helium high to really discover the superconductor phenomenon. So the liquid helium can achieve as low as around 4 Kelvin. 4 Kelvin. And of course, you need to manipulate the pressure. Then you can even achieve a even lower temperature. So the superconductor might be useful for the something like the quantum computing, something like that, but it will be really difficult. So we will not cover it, just try to natural the classification of the materials only. Okay, so let me come back. So go back to the previous two setup. Okay, so here we talk about what is charged particles. Okay, so it says the property of conductor and insulator are due to the structure and electrical nature of atoms. So in high school chemistry, you know an atom, 原子. So for an atom, it should have a nucleus. So this is the nucleus, and then there will be some electron rotating around the nucleus to form an atom. So depends on what element it is. It has different number of so-called proton, neutron, and also electron. And in chemistry class, you know that the number of protons should be equal to the number of electrons, so that it has perfectly neutral electricity. So it says the property of the conductor and insulator are due to the atom consists of positive charge protons, negative charge electrons, and they are the amount of them are actually the same. So the atom are electrically neutral, and also there will be some neutrons. The neutrons have the same mass, almost the same mass as the protons, but it is electrically neutral. Okay, so the proton and neutron are packed tightly together in the central nucleus. So here we will have some proton and neutron there. So proton is a positive charge, and yeah, neutron is neutral. Okay, so yeah, so like that. So yeah, and actually the central nucleus and do not move. And here we will also find that when the atom of the conductor like copper come together to form the solid, which means we have many like copper atoms, then actually the nuclear lattice cannot move. They can only oscillate within the lattice, and the thing they can move are the free electrons. Okay, some of the outermost and most loosely held electrons become free to wander about within the solid, leaving behind positive charge atoms. So we'll call them mobile electron, the conduction electron, or free electrons. Okay. And in the non-conductor or insulator, there are few free electrons. Yeah, not necessarily zero, but there are actually few electrons in the insulator. Okay, so here we also try to mention another concept called the induced charge. Induced charge. In Chinese, it is called 感应电荷 induced charge. Okay, so here it says a neutral copper in the bottom right figure. So there is a neutral copper. Although you see some positive sign and also some negative sign throughout the copper rod, but we call it neutral, which means that the total charge amount over the copper rod is zero or near zero. Okay, so a neutral rod is electrically isolated from the surroundings. Yeah, so around it is just air. So we know that the air is an isolator. So we don't expect any charge can go from outside to the rod or going out from the rod. So there will be no charge can going in or going out. So either end of the copper rod, yeah. So yeah, by being suspended on a long conducting thread. So we try to hang it here. So this is the copper rod. Okay, so here we try to have this plastic rod, and just as what we have mentioned in previous slide, if we have a plastic rod, rub it with fur, then it will have negative charge. And we try to put this rod close to the neutral copper, there will be induced charge, which means that, so for this rod, for sure, we have some negative charge. And there will induce some positive charge if you just place this negative charge close to the neutral copper rod. So these are so-called the induced charge. Induced charges. Okay, but of course the total charge amount should be zero. So on this side we have positive induced charge. On the other end we will have the negative induced charge to balance the total charge amount to be zero. Okay, so here, yeah, the reason is that just I mentioned is that the nuclei are positive charge and they are not free to move. They will be just oscillate within the lattice. So the positive charge are not free to move. So when you place the negative charge rod close to the copper rod, the free electron will be repelled by the plastic rod. So the negative charge cannot go outside, So it can only go to this side to repel by this rod. So in this sense, as much as the negative charge electron go to this side, the remaining charge will be positive charge, which are the nuclear, come from the nuclear. Okay, so we will have induced positive charge in this side and induced negative charge and on the other side. So, and then that negative charge attract the remaining positive charge. So in this case, we have negative charge going to the other side, and then we have positive sign remain here. So opposite sign of charges will attract each other. So in that case, we will see these two rods attracting each other. So that's another phenomenon. You can consider is the third setup about the induced charge. For the previous two setup, it tells you there should be something called positive charge, something about the negative charge. And then here, for the conductor, we will have induced charge. Of course, for isolator, we don't have this phenomenon because for these two cases, glass and plastic are isolator or non-conductor. So there will not be any induced charge. So if you just put it there, then the positive charge cannot go, and then the negative charge can not go either, cannot go away either. So for isolator, there will be no or almost no free electron to move. But for conductor, we'll have free electron so that it can generate some induced charges. Okay, so far any questions? Okay, no questions. And then, so here, we try to talk about what is charges. And yeah, so this definition is a bit strange. Usually when we try to define a physical variables, we usually would try to write this variable equals something. But for this one, it is not this case. We try to define what is charges, what is charge. But here, Q is the charge. But yeah, as you can see here, this is the derivative of the charge with respect to time equals the current. And at this moment, you don't really know what is a current yet, but this is so far the definition. So I is the current, Q is the charge. So you take the derivative of the charge with respect to the time, then it will be the current. It will be the current. Okay, so I suppose you have learned the calculus 1, so you know what is derivative, or even in high school mathematics, you should have know what is derivative and also integration, I suppose. And I should say in physics class, or even in engineering class, the most important thing, one of the most important thing is the SI unit. SI unit is very, 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 very important. Okay, so you actually need to remember, you actually need to memorize the SI unit for different variable. Yeah, at least the common the common variable. So yeah, so that you can use some equation to try to construct some composite SI unit. What I mean is that for the charge, you really need to remember the SI unit for the charge is Coulomb. The short form is of course C, Coulomb. Okay, so this is what you really need to remember. And yeah, and for the current, the SI unit will be A, ampere. A is ampere. Okay. Ampere is the SI unit for the current. It's the SI unit for the current. So this, which means that if you have a current of 1 ampere and the current flows for 1 second, then the charge amount of the change of charge amount will be 1 Coulomb. 1 Coulomb. So actually, you can just plug all the SI unit like 1 Coulomb. 1 Coulomb is 1A times 1S, or you can regard it as Q equals I times T, or maybe delta. Put it like delta. The change of charge amount will be the current going in or going out, and for the delta T amount of time, then the amount of charge changing will be delta Q. So the SI unit for delta Q is Coulomb, and then this is A. So this is C, this is A, the time should be S. So usually they will not write it like this, but I think it is fine. Or of course you can just try to write it like this, then it will be no problem. So this is the way you try to construct some composite SI unit for some of the variables. Yeah, you don't really need to remember it one by one, but for the fundamental SI unit, you really need to remember. Of course, for the time, you must know what it is S, but for charge, it should be Coulomb. For the ampere, for the current, it should be ampere. And maybe in the next time, next chapter, you will learn the electric field. Then it will be Newton per Newton per meter. Newton per meter. Newton per Newton per Coulomb. Newton per Coulomb. Then yeah, you have some equation to remember what it is. Okay, so this is the introduction, brief introduction about the charge. So here comes the main part of the chapter, which is about the Coulomb's law, Coulomb 定律. Okay, it says the Coulomb's law describes the electrostatic force or electric force. So electrostatic force is 静电力. Electrostatic force. So electro is den, and then static is 静态, and then force is 力. Okay, so electrostatic force is 静电力. Okay, so between two charged particles, if the particles have charges Q1 and Q2 are separated by distance r and are at rest or moving only slowly relative to each other, then the magnitude of the force acting on each due to the other is given by this equation. So this is so-called the Coulomb's law. I suppose you should have learned it in high school. But yeah, of course, here we just write it in the vector form. So the force is of course a vector. And of course, in physics 1 or even in high school physics, you know what is a force. And the force with a SI unit of Newton. And then, yeah, here on the right side, we have something called 1/4 pi epsilon naught, and then multiplied by Q1, Q2 over R squared. and then this one is called the unit vector. Unit vector. R hat is a unit vector in the like the spherical coordinate. SPHE. Spherical coordinate. Spherical coordinate. Okay, so let me try to explain. Yeah, so epsilon naught is a constant called the permittivity constant. Permittivity constant. Yeah. Okay, so this number is actually 8.85 times 10 to minus 12. 8.8 times 10 to minus 12. Of course, with a very complicated SI unit. Of course, you don't really need to remember it, because if you can remember this Coulomb's law, or maybe in the scalar form like F equals 1 over 4 pi epsilon naught times Q1, Q2, you can just write it as a Q square and then over R square. Or maybe let's just make it like generalized. Okay, so for the F, it has a SI unit of a Newton. And 4 pi, it doesn't have any SI unit. It's just a constant. So we have the SI unit for the epsilon naught. And then for the Q, the charge, the SI unit should be Coulomb. So we have C square. And then for the distance, the SI unit should be meter. So we have meter square. And then you can quickly find that the SI unit for the epsilon will be n times meter square over C square, something like that. Or should be the other way around. Should be the other way around. Should be the other way around, because I move it to there and move it to here. So it should be C square over n over meter square, like this. Should be the other way around. Okay, so you don't really need to remember it. And actually, we also define another constant, call it K, because in the electrostatic or even in electrodynamics, usually 1 over 4 pi epsilon naught are occurring together as a constant, as a composite constant. It usually occur together. So we also try to define 1 over 4 pi epsilon naught as the electrostatic constant, or the Coulomb's constant. I don't remember this name. So I usually call it the K. And this K is nothing but 8.99 times 10 to the 9th power. And of course, the SI unit is the other way around, because 4 pi doesn't have any SI unit. And so the SI unit, it should be the reciprocal. The SI unit for K should be the reciprocal of the epsilon naught. Okay, so generally I will just remember this number. Maybe you don't remember, but it's fine. In the quiz or exam, I will just give you some of the constants, so you don't really need to remember the number. But as I teach this course, I usually write this constant, so I already remember this number, because there are not much number to remember. So yeah, remember that are not so difficult. Okay, so here we have K equals 1 over 4 pi epsilon naught. So this is a brief introduction about the Coulomb's law. Okay, so let me try to explain what does it mean by this equation. Okay, so actually for this Coulomb's law, there are some interesting interesting insight within this equation or within this formula. Actually, in the previous slide, we use 1/4 pi epsilon rather than k, but here, actually, we already define k is 1/4 pi epsilon. So we just write it as this expression. Okay, so for the Coulomb's law, there are, okay, so let me check back here. So for the Coulomb's law, it tried to describe the forces. Of course, this force is called the electrostatic force. So it tried to quantize how large is the force between two charged particles. So the force is proportional to the product of the charge amount of the two charges. Okay, and then it is inversely proportional to the distance, distance square, the square of the distance. Okay, so this is the magnitude. This is the magnitude. So we have this constant is the k, and then multiply by the product of the charge amount, and then divide by the square of the distance. So this is the how we try to calculate the force. How we try to calculate the force, and then, of course, here it is the vector form. The vector form. The vector form means you don't only have the magnitude, but also the direction. So here you can see that there are, and yeah, actually in the previous slide, it talks about the force acting between two charged particles. So within this, there are totally 4 cases, because the charge can be either positive or negative for two charges. So there will be 2 to the second power, which is 4 cases. But of course, 2 of them are quite similar. So here we only solve 3 cases. So the first case is that both of the charge are positive charge. Both of the charge are positive charge. So here, this is F. This is F. Okay. So here we will try to define the direction of the direction and the magnitude of the R hat. This is called R hat. So as I mentioned, this is the unit vector of R. So when you consider this charge as the original point, 原点, and then you try to consider the force acting on this one, then you will have the R axis. You will have the R axis. R axis like this. R axis in this direction. When you consider this charge, from this charge to this charge, so this is the R axis direction. So in that case, R hat is this one. R hat is this one. Okay, and when we consider R hat is a unit vector, R hat is a unit vector, which means that the magnitude of this unit vector should be 1. So this is the amplitude, the magnitude or the absolute value should be 1. Okay, so this is R hat. Okay, so this is R hat, and we try to plug it in this equation. So R hat point to the right side for figure A, and then Q1, Q2 are positive value. R squared should be a positive value, and then K is 1/4 pi epsilon is also a positive value. So if Q1 and Q2 are positive, then F this one should also be positive. This one, or at least this term is positive. So it leads to k times q1 q2 over r squared is also positive, which means that the direction of f should be the same as r hat. And in this sense, you can see f has the same direction as f. And of course, this is longer, maybe longer or shorter, depends on how large the force is. But yeah, f and r hat should have the same direction. Okay, and then if you try to consider the other way around, you try to consider from this charge to this charge, then in that case, the direction of our axis is the other way around. Okay, so this is the direction of our axis from this charge to this charge. And in that case, our head points to the opposite direction. So for this charge, our head points to the left side. For this charge, our head points to the right side. And then you still plug in the same equation, q1, q2, r squared, and then k. All the values should be the same, but the r hat for this charge and r hat for this charge are different. So f should have the same direction as r hat, but different r hat. This is the red r hat. This is the blue r hat. So the red r hat for the left charge, the blue r hat is for the right charge. Okay, so f is this vector should have the same direction as the red r hat. So in this case, for this charge, the f point to the left side. For this charge, the f point to the right side. So which means that these two charges repel each other. Okay, so they repel each other. So they repel each other. Okay, so the next case is Q1 is positive, Q2 is negative. And also it includes Q1 is negative, Q2 is positive. No. For the second one is not positive, negative. Okay, so for the second case, Q1, Q2 are all negative. Q1, Q2 are all negative. So you can see negative charge, negative charge. Okay, so when you consider this charge acting on the other charge, so the r axis is point to the right side. Okay, so r hat points to this direction. Okay, so here when you try to plug in Q1, Q2, r squared, and k in the Coulomb's law. Okay, Q1, Q2 are all negative, but negative times negative is positive. So the whole terms k times Q1, Q2 over r squared is still positive. It's still positive because negative times negative is positive. Okay, so this whole term is still positive, which means that f has the same direction as r hat. And similarly for the other charge, when you consider the force from this one to this one, the r axis is pointing to this side, pointing to the left side. And in that case, r hat point to the left side, and f is also pointing to the left side. Okay, so as much as this term is positive, f has the same direction as the r hat. Sorry, this is r hat, not r vector. R hat. This should be r hat. So f should have the same direction as r hat. So the f for the left charge points to the left side, and the force acting on the right charge points to the right side. Okay, so still they repel each other. They repel each other. Okay, so for the third case, here we have Q1, Q2. One is positive, one is negative. And actually, if Q1 is negative, Q2 is positive, it is actually the same. So it doesn't draw it again. Okay, so here, if you try to plug in Q1, Q2 into here, you can easily find that K times Q1, Q2 over R squared. This whole term is negative. This whole term is negative because one of them is negative, one of them is positive. So this is negative, this is positive, this is positive. So the whole term is negative. Okay, so the whole term is negative, which means that the force should have the opposite direction with the R hat. So here, when we consider the force from the left charge acting on the right one, okay, we can see that the R axis still point to the right side. Okay, R axis doesn't change at all. So R axis from the left charges to the right charges. The R axis point to the right side, always point to the right side. And in that case, R hat point to the right side for the right charges. And in that case, F point to the opposite direction because K times Q1, Q2 over R squared is negative. So F points to the opposite direction to the R hat. And similarly, when we consider the force from the right charges acting on the left charges, here, the R axis point to the left side and R hat point to the left side also. So in that case, F point to the opposite direction to the R hat. Okay, so the axis for the three case doesn't change, but within the same case, the R axis points to the opposite direction. Okay, for the right one, for the right charges, R hat point to the right side. For the left charge, R hat point to the left side. So this is something tricky in Cartesian coordinate, like the XY coordinate. Cartesian. From the Cartesian coordinate, you can never imagine, oh, so the unit vector for the x-axis should always point to the right side. The unit axis for the y-axis, j hat always point to the upper side. But for spherical coordinate, it is not the case. It is not the case. Yeah, the r-axis can point to different direction. Okay, so this is the first point you need to know. Okay, and actually this is the punchline for this equation. No matter what polarity of the Q1 and Q2 is, then it also fit these rules. Okay, so just now we mentioned the charge. I mean the electrostatic force between two charges. So if we have more than two charges, what will it be? The case is that if we have more than two charges, and then we need to consider the electrostatic forces, then we need to consider separately, which means if we have n charges, like for example, if we have 1, 2, 3, 4, this is Q1, Q2, Q3, Q4. Okay. If we need to consider the net charge acting on the, just say Q1, Of course, you can also try to consider the net force acting on Q2, Q3, or Q4 either. But yeah, just for instance, if we try to consider the electrostatic force for Q1, then you really need to consider electrostatic force between charge 1 and 2, charge 1 and 3, so on and so forth, up to charge 1 and charge to charge n. Okay, which means that for this case, you need if we have 4 charges, then we need to consider let's say F12, F13, F14. Yeah, they might not be attracting each other. Maybe some of them are repelling each other. Let's say F13 points to the opposite side. So maybe some of them points to each other, some of them point repelling each other. Okay, we need to find the force one by one, and then we try to add them together with the vector sum, which means that you need to decomposite the force in just say x-axis and y-axis, and you try to add the x-axis component and y-axis component together to find the vector sum. Okay, so which means that if multiple electrostatic force act on the particle, the net force is the vector sum of the individual forces. So you need to find one by one, add them together. Okay, so here we try to explain another theory called the shell theory. So far, I will not, I cannot show you the proof yet. I will show you the proof, I think, in chapter 23, two chapters later. With the Gauss law, I can really try to explain why the shell theorem would be like this. But here, just try to accept the conclusion here. Okay, so for the shell theories, actually it has 2 substatements. The first one is that a charged particle outside a shell with charge uniform distributed on its surface is attract or repel as if the shell charge were concentrated as the particle as its center. Okay, so it looks quite complicated. So let me try to explain it with a figure. So it says, if you have a sphere, yeah, outside a shell, you can imagine it is a sphere, 球体, it is a sphere, and then all the charge are equally distributed on the surface. Actually, it should be a 3D sphere, but if I just draw it here, then you might feel confused. But actually, it should be a 3D sphere. It should be a 3D one. So it is a 整个球体 the whole sphere, and then if we assume this is a perfect sphere, and then the charge is distributed evenly or uniformly. Uniformly distributed outside a shell. Uniformly distributed means 均匀分布。均匀分布。Uniformly distributed on the surface, and is attract or repel as if its charge were concentrated as a particle as its center, which means that if the total charge, we call it Q. So if we just put another charge, small q0 here, if it is positive or negative, it doesn't matter. Maybe if we assume it is positive, then of course they will attract each other. according to the Coulomb's force. But for the second case, is that if you replace this one with just a point charge, and this charge is capital Q, is still capital Q, we doesn't really change the charge amount. We try to concentrate all the charge on the surface to the radius. Yeah, to the radius. We try to put all the charge to the radius, to the I mean the center, to the center of the sphere. And of course, this distance is capital is small r, and then still we have this Q0, plus or negative is okay. Then of course, if it is still plus Q0, then of course they will attract each other. Maybe I can use another. Sorry. Can use another color. So this is F, the Coulomb's force. Attracting each other. This is the F. Maybe I call it F1. This is F1. This is F2. This is F2. Okay, and the shell theorem 1 tells you that shell theorem 1 tells you that F1 should be the same as F2. If we just try to replace all the charge to its center, okay, so it will attract, or if it is negative, just say if it is negative, then of course they will repel each other. If it is negative, they will repel each other. F1, like this. But the shell theorem 1 tells you that these two forces will be the same. So it tells you that a charged particle outside a shell with the charge uniform distributed on the surface is attracted or repelled as if shell charge were concentrated as a particle at its center. So we try to put all the charge to the center. It will be actually the same. If you consider or put a charge nearby, okay, the phenomenon will be the same. Okay, so this is shell theorem 1. For the shell theorem 2, or the shell theory 2, a charged particle inside a shell with the charge uniform distributed on its surface has no net force acting on it due to the shell. This means that if we have a sphere, okay, we have some charge on the surface. Okay, so maybe positive charge or negative is okay. And then if we place, of course, this is still a 3D sphere. Sphere. And then if we try to put a charge inside the sphere, okay, of course, this one is outside the sphere. This one should be inside the sphere. It tells you that no matter which point this charge is at, whenever it is inside the sphere, then the force acting on this charge will be 0. There will be no net force acting on a charge inside a uniform electrical uniform sphere. Okay, this is the shell theorem 2. Shell theorem 2. Okay, so it says a charged particle inside a shell with the charge uniform distributed on its surface, has no net force acting on it due to the shell. It doesn't necessarily at the center, and as much as it is inside the sphere, it will be okay. You may feel strange, but you can try to consider it like, for example, this is the center. You try to connect this part. So at least the left part and the right part are symmetric. Not necessary. Not necessary. Yeah. It should be symmetric, because for this one, and for this one, if you find the symmetric point, the horizontal component will cancel each other, clearly. But for the vertical component, yeah, it is not so trivial. And of course, the proof is not so easy. It's not so easy. It's not easy at all. But you can imagine that if this point is close to the top part, so here, this segment is shorter than this segment. However, the distance is that this part is closer to this point, this part is comparatively farther. For example, for this part, this is quite far away from that point. So when you try to add the vertical component of this part and also the vertical component of this part, the self-theorem tells you that they will perfectly cancel each other. So yeah, if you don't believe, you can try to use some calculus to calculate about it, but I am afraid it would be very difficult to do this integration. But yeah, so far, so you try to accept this conclusion, I think. And in chapter 23, I'll try to show you why with the Gauss law. But of course, Gauss law is a law, so we don't have a proof for it. You may also like to ask why the law is true, but yeah. You know, the law in physics is like, yeah, it is always true as much as you find all the phenomenon matches the law, then the law is correct, unless you can find a counterexample, then you can disprove the law. But of course, the law is built hundreds of years ago, so up till now there is no counterexample. So yeah, you should believe the law is correct. Okay, so here is a quick checkpoint. It asks, the figure shows 2 protons and 1 electron on the x-axis, on an axis. So on the central portion, what is the direction of the force due to the electron? Yeah, so it asks you on the central proton, what is the direction of the force due to the electron? So this is a negative charge. This is a negative charge. This is a negative charge. This is a positive charge. So these two will attract each other. So in that case, this point to the left side. Okay, so for the part B, the force due to the other proton. So this is positive. This is also positive. They should repel each other. So in that case, they repel each other. So it also point to the left side for the middle proton. And the net force, because we need to add these two together, both of them point to the left side. So the total force is also pointing to the left side. So for this one, left for all the 3 questions. Okay, maybe I think we stop here today. So before finishing, if you have any questions. Okay, so if you have no question, we dismiss the class now. And if you have further question, you may feel free to ask via WeChat or yeah.